Hello, welcome to a problem session in introductory physics. Okay, I've been gone for a while, but let's see if I can get back to my doing problems again. So here is a good problem, and it requires you to understand a lot of different things. So if you can do this problem, go ahead and do it. Pause the video and go ahead and do it, and then come back to it. Otherwise, let's see what kind of things we would need to solve this problem. One thing to notice is we have something called a steady current, right? Steady current. So you should know what steady current means. Steady current is basically current that's not changing in time. So if there's a current I, is independent of time. So that's what steady current is. So when turn the switch on in a circuit, the current initially is changing with time, but then it stabilizes, and that's the steady current. So in this situation, it will have same current in both wires, because the same wire. So if you look at in this situation, you have two different wires. So how current going here is going to get out here. Okay, so this will have I1 is equal to I2. Now you need to know what the current means. So this the current is basically, if I stay here and if I ask how much charge is flowing past me per unit time. So I is basically at say point X, at X, which is the same as all the points, but let's look at just point X, is delta Q passing through me, through the entire area of cross section over in time delta T. So this is not charge itself, but the flow of the charge. So it's looking at the rate at which charge, not the speed with which charge is flowing, but the rate at which charge is moving across me. How much charge per unit time. So you can convert this into a speed by introducing what is called a density of current. So let's look at this. So if there was a drift, if the charge, say there was some charge Q, which happens to be electron here in metals, but it can be a hole in semiconductor, like a p-type semiconductor. So this is a moving, and say it's drift velocity d. It's not the actual velocity, right? Because in metal, when not all electrons, but the conducting electrons can move at very high speed, but they are bumping into nucleus and other electrons, and there's velocity is there's overall velocity is called drift velocity. So this is the drift velocity, which is very small, much smaller than the actual speed which electrons are moving. So this is drift speed or drift velocity, if you're talking about direction also. So if I assume that this is constant, then in time delta t, all of these charges would move past it, right? That's the way you can think about it. So if there are NE, so this electrons, NE per unit volume, and these are conducting electrons. So if you look at copper, there's only one electron per atom that's conducting. Then this will be like how many copper atoms per unit volume. So that's how many electrons there will be. It's pretty large numbers usually, So you may want to compute using the density of copper atoms in there. But suppose I have this as per unit volume, and so all the things in this volume would have crossed me, right? So this NE times, what's the volume? V times VD, area of cross section is A times delta T, would have crossed it in delta time, and divide by delta T. So this will be the current, this will be the I, and you can see that you have NE, VD, and area of cross section. Area of cross section varies from wire to wire, but these are kind of internal properties, right? So this internal property, this thing is given a new name, a new symbol. This is per unit area of cross section, and this whole current density. And so this will be just depending on what material you are and the speed with which the electrons are flowing in that material in terms of drift speed. So you might say this is I is actually J times A. This is a good formula to remember. And when it comes to Ohm's law, there's another thing you need to know. So there are several ways you know Ohm's law. You probably know the Ohm's law as a voltage drop equals to current times the resistance. V equals IR, right? If you think in terms of not I, but in terms of J, then this will be voltage drop is equal to I with a current times A, and the resistance will be some kind of resistivity times length of the wire times the area of cross section. So you can this is the resistivity, how long the wire is, how wide the wire. So resistance is small, thicker the wire, longer the wire. So this, you probably remember this. This is a formula for resistance, and this rho is 1 over conductivity. So this is conductivity. So these are some of the things that you might need to solve this problem. So you have a delta V, so A can cancel out, and you can see that I can bring the length of the wire, so delta V over, that's the voltage that dropped across the wire, and equal to rho can be written as sigma. I can write 1 over sigma times J. Now this is the electric field in the wire. So this, the electric field is how much voltage over length, and so this is 1 over sigma times J. So another way to write Ohm's law is J is equal to sigma times E, and this is point by point you can write down, and this is like overall, and this is internally at each point. So there are two ways to think about Ohm's law, and this problem actually uses both of them. Okay, so now that you know the background, let's try to do the problem, right? Okay, so to the problem 1, we have the wire which is going from here to there. So we can have a resistance of wire 1 plus resistance of wire 2. That will be they are in line, in series, so that's the net resistance, and each resistance is like a 1 over conductivity of that wire plus in times of length of the wire, the area of the wire. So those are the resistances, and so the same current is going to flow, and the voltage across the entire thing is V0. So delta V over resistance, that should be the answer, right? So let's complete this. This is going to be V0, and you have a 1 over sigma 1, L1 over the area of cross section is the same, plus 1 over sigma 2 L2 with the area of cross section same. So that's the answer for 1. There's a steady current is this, so that's the answer. So let's look at the electric field. To look at the electric field, we use the electric field over here. So electric field 1 will be current density 1 over sigma 1 times the current density that goes through 1, right? So what's the current density? Current density is related to the current. J1 times the area is the current in 1. So you can already see that J at 1 was conductivity, whatever the density of electron is 1 times the drift velocity in 1. Okay. So you can now, although you know this, but this is not necessary to solve this problem. This J1 is just simply I1 over A. So 1 over sigma 1 I1 over A. So that's the answer. The electric field is going to be over here, because we are just dealing with sigma and sigma 2. And if we were dealing with more detail, like a number density of the conducting electrons and the drift velocity, we can get that from this formula also. If those were the question, you can help you do that also. Let me clean up a little bit. Okay, so, and then you can get E2. E2 will be, because this is the positive side, E2 will be in that way, is the E1, and E2 would be pointed in that direction. So E2 will be, you can see the same argument can give me 1 over sigma 2. I1 is just I, is the same I as that, times I over A. So it's the same, except they're different, right? So you can see that E1 is not equal to E2. So we have a surface here. On this side of the surface is E1, and this side of the surface is E2. And you can try to imagine that this is like an infinitely big surface, and if it is a sigma, then you charge density was sigma 0, say charge density, then you will have electric field. This will come from an idea which you might have used before. So say you have a very large charge density sigma 0, very large area with charge density sigmas, this is some large plate, large sheet of charge, then you know the electric field over here and electric field over there. So like this will be E equal to sigma 0 over 2 epsilon naught, and this will be again pointing that way, so this is plus, and E equals to sigma 0 over 2 epsilon naught, pointed this way. So difference between them actually gives you the charge density. So sigma over 2 epsilon naught minus sigma over 2 epsilon naught, sigma 0, sigma 0. That is the so you have a sigma 0 over epsilon naught. This is the difference in the electric field on the two sides. So sigma 0 can be simply obtained by epsilon naught times difference in electric field on the two sides. We can apply the same thing over here. We have E2 and E1, and so you can take this as a positive direction. Both are positive. So sigma charge density, that's number 4 to answer this guy. Charge density is equal to E2 minus E0 times epsilon naught. and you got this, so we can just fill it in. A and I are common, so you have a 1 over sigma 1 minus 1 over sigma 2. This is the charge density, and these sigmas are conductivities. Okay, how about, so we got the electric field, we got this, we got this. How about the electric potential at right in the middle? Well, let me clean up and then do that. Okay, so you can do it a couple of different ways. You can use your knowledge of series and then say, okay, if V0, how much potential dropped here? If this 0, how much potential dropped here? So if we look at the drop in the potential across here from, and then that can be just done simply. So 2 ways. One is, so this is number 3. Voltage at X would have to drop across here, right? So we already know the current. We know the current. So if the current is going between here is this I, and the resistance is R2, then the V at X will be I times this R2, because Vx minus 0 across there. So that's one answer. We can just get this I from here, and R2 corresponding to that, and that's the answer. Or you can say, I want to integrate this electric field E2, and that should give me the voltage. So the length of the two times this E2 will give me the voltage at X minus V0. So this will be L2 1 over sigma 2 I over A. Both of these will be exactly the same answer. But I just want to show you that there are 2 ways to do it, this way and this way. So that got the 3 also. Okay, so we've done a whole lot of different concepts and then solve this problem. I'm going to stop here. If you like this video, please don't forget to hit the like button. If you need to study more physics, you can go to my website here, www.physicsbootcamp.org, and you can subscribe and tell your friends about this channel. That will help us distribute this material more widely. Thank you, and bye.